Hello friends, welcome you all to the 43rd lecture on function analysis and its applications. In this lecture, we will discuss the conjugate of an operator. The content of today's lecture is the conjugate of an operator. Definition of conjugate of an operator. Let x and y be normed spaces. Let T such that x to y be bounded linear operator or bounded linear transformation. Then the adjoint T star of T is defined as T star such that y star to x star given by T star f x equal to f of Tx for all x belonging to x and f belonging to y star. Here the continuity of T and f shows that T star is continuous. Okay. Here the mapping T such that x to y. For all x belonging to x, then Tx is the element of y. If f is the bounded linear functional, f belonging to y star is the adjoint of y. Then T star such that y star to x star. That is meaning of T star f as here T star f defined f of Tx. Meaning of this is f composition Tx. Okay. That is T star f x equal to f of Tx. And f belonging to y star and x is the element of x. The adjoint operator T star satisfies the property that x belonging to capital X and f equal to y that is the sequence yn is the element of y star. Then inner product of T star f and x is equal to inner product of f and Tx. For all T star f, here f is the element of y star. Okay. So f is the element of y star. Then T star f is the element of x star. Okay. And here x is the element of x, then Tx is the element of y. Okay. Then inner product of y Tx, y that is f equal to summation n is equal to 1 to infinity y n, that is sequence of y and the sequence of Tx. This is the classical definition of inner product. For example, let T such that C0 to C0 be defined by Tx is equal to xn by n, where x, that is sequence xn, is the element of C0. Then find the adjoint T star. So here already we have proved this example as bounded linear transformation or bounded linear operator. Okay. So here avoiding to prove the linearity of this transformation. Okay. So here norm of Tx, here Tx defined xn by n, that is xn is the element of C0, that is the norm defined as L infinity. Okay. So norm L infinity defined as the supremum of the sequence of x, that is xn. So here sequence of Tx is xn by n. that is norm of Tx is equal to supremum of mod xn by n. Okay, n belonging to natural number. Okay, so if n is equal to 1, that is, this is the max value. Hence, this less or equal to supremum of mod xn. Okay, so supremum of mod xn defined in L infinity norm. So xn belonging to L infinity, that is the norm x in infinity norm. Okay. What is C0? C0 is the space of all sequences of complex number which converges to 0. Okay, so norm of Tx less or equal to norm of x, that is T is bounded linear transformation. So now we have to find T star. Okay, so here mapping T such that C0 to C0. Okay, so C0 equivalent to L infinity norm. Okay, so conjugate of C0 is L1. Okay, then mapping T star such that L1 to L1, because here T such that C0 to C0. Here mapping T such that X to Y, then T star such that Y star to X star. Okay, so here C0 star is L1 and also C0 star is L1. So mapping T star such that L1 to L1. Okay, for F belonging to L1, that is Y belonging to L1 and X belonging to C0, we have the inner product of T star F and Xn. Okay, as per this definition, inner product of the T star F Xn, that is T star F of X. Okay, meaning of this is this, and T star Fx is equal to F of Tx as per the definition of adjoint. Okay, from here. So Tx is Xn by n. So we can write F of Xn by n. So this can be written as inner product of F and Xn by n as per this. F of Tx, that is inner product of F of Tx. Okay, so F is Y, that is Yn. So we can write this is inner product of Yn and Xn by n. So as per the usual definition of inner product, we can write summation n is equal to 1 to infinity Yn into Xn by n. Okay, so this is scalar, this is also scalar, so we can write summation n is equal to 1 to infinity Yn by n into Xn. Again, using the usual definition of inner product, this can be written as inner product of Yn by n and Xn. So if you compare this inner product and this inner product, that is T star F is equal to Yn by n. Okay. Similarly, next example, let T such that L1 to L1 be defined by Tx is equal to 0, x1, x2 and so on. Then find the adjoint of T star. Here mapping T such that L1 to L1, the dual of L1 is L infinity. Okay, so this one. Then the mapping T star from L infinity to L infinity, dual of L1 to dual of L1, that is T star such that L infinity to L infinity. For F is equal to Y, that is sequence Yn belonging to L infinity and X belonging to L1, Then as above, we can write inner product of T star f xn equal to T star f of x. Meaning of this is this. And T star f x can be written as f of tx. So f of tx can be written as inner product of f and tx. F is y, that is inner product of y and tx. So as per the usual definition of inner product, that is y1 into tx1 plus y2 into tx2 and so on. So here tx is 0, x1, x2 and so on, and y is y1, y2 and so on. So inner product of ytx can be written as y1 into 0 plus y2 into x1 plus y3 into x3 and so on. That is, this can be written as in summation n is equal to 1 to infinity y n plus 1 into xn. That is summation n is equal to 1 to infinity y n plus 1 into xn. Again, this can be written as in inner product of y n plus 1 and xn. Okay, so comparing this inner product with this, that is T star f equal to yn plus 1. Here T is known as the right shift operator. Okay. Theorem, let T such that x to y be a bounded linear operator on a normed space x to a normed space y, then T star such that y star to x star is given by T star f x is equal to f of tx for all x belonging to x and f belonging to y star. Then T star is bounded linear transformation. Then the mapping T to T star given by psi such that bxy to by star x star. Bxy means set of all bounded linear transformation from x to y. Similarly, this one, set of all bounded linear transformation from the adjoint y star to adjoint x star, such that psi t is equal to t star for all f belonging to bxy is a linear isometry on bxy to by star x star. Moreover, the mapping T to T star reverses the products and preserves the identity. Let us prove it one by one. We have to prove T star is a bounded linear transformation. Okay, so first we prove T star is linear. For any x belonging to x and f and g belonging to y star, we have T star f plus gx. Okay, this can be written as f plus g of tx as per the definition of adjoint. So meaning of this is f of tx plus g of tx. Again, using the definition of adjoint, f of tx can be written as T star f x and this is T star gx. That is T star f plus T star g x, we can write. Therefore, T star of f plus g is equal to T star of f plus T star of g. Also, for any scalar alpha, T star alpha f x equal to alpha f of tx as per the definition of adjoint. Meaning of this is alpha into f of tx, that alpha is scalar. Again, f of tx can be written as T star f x as per the definition of adjoint. Hence T star alpha f x equal to alpha into T star f of x. Therefore, T star of alpha f equal to alpha into T star f. Hence, from 1 and 2 prove that T star is linear. Now, T star is bounded. So, T star f x is f of Tx. Okay, we know that this one by the definition of adjoint. So, taking the modulus of both sides, that is modulus of the T star f x is equal to modulus of f of Tx. F is functional, so this can be written as less or equal to norm of f into norm of Tx as per the definition of bounded linear functional. Okay, here T is bounded linear transformation or bounded linear operator. Then this can be written as less or equal to norm of T into norm of x. That is modulus of T star f of x less or equal to norm of f into norm of T into norm of x. Now dividing this inequality by norm x and using the property norm f is equal to supremum of the mod fx upon norm x, then this upon norm x can be written as norm of T star f less or equal to norm f into norm T. Okay, again we divide it by norm of f. Okay, and using this definition, then this implies that norm T star f upon norm f, that is norm of T star, and this is right side norm of T, that is norm of T star less or equal to norm of T. So norm T is already bounded linear transformation, that is less than infinity. So norm of T star less than infinity, hence T star is a bounded linear transformation. Now we have one result. If X is normed space, then for each non-zero vector x0 belonging to x, then there exists a functional f0 on x such that norm f0 is equal to 1 and f0 of x0 is equal to norm of x0. We will prove it later on. There exists f belonging to y star with, as per this result, norm f is equal to 1 such that f of Tx is equal to norm of Tx as per this result. Hence, norm of T is equal to supremum of norm Tx upon norm of x such that x not equal to 0 as per the definition of bounded linear transformation. So here norm of Tx is equal to f of Tx. So this can be written as mod of f of Tx upon norm of x such that norm f is equal to 1. So we can write this is in mod because this is the positive value. Okay, so we can write this in mod. As per the definition of adjoint, f of Tx can be written as T star of fx. Okay, this is written in norm because f is bounded linear function, so we can define it mod, and T star is bounded linear transformation, so it is defined in norm. Okay, so as per the bounded linear transformation, this is less or equal to norm of T star f into norm of x. So norm x and norm x cancel out. So we have supremum of the norm T star f such that norm f is equal to 1. Again, as per the definition of boundary linear transformation, this can be written as norm of T star. Okay. So here norm T less or equal to norm of T star. From 3 and 5 we get norm of T is equal to norm of T star, because here in 3 norm T star less or equal to norm T, and in 5 just reverse. Okay. So here norm T less or equal to norm T star. So as per 3 and 5 we have norm T equal to norm T star. The isometric character of psi followed by equation 6. Okay. So in the statement here psi t is equal to T star. So here norm of psi t equal to norm of T star, and norm of T star is norm of T. That is norm of psi t is equal to norm of T star equal to norm of T. So this is the isometric character. Now we prove psi is linear and 1 to 1. Let alpha beta be scalars. We have star of alpha t1 plus beta t2 f x equal to f of alpha t1 plus beta t2 x as per the definition of adjoint. This can be written as f of alpha t1 x plus beta t2 x. We know that f is linear functional. So this can be written as alpha into f of t1x plus beta into f of t2x. Again, as per the definition of adjoint, this can be written as alpha into t1 star of fx. Similarly, this plus beta into T2 star f of x. Okay. Again, this can be written as alpha T1 star f plus beta T2 star f x. So comparing this and this, we can write star of alpha T1 plus beta T2 equal to alpha T1 star f plus beta T2 star f. Again, this can be written as alpha T1 star plus beta T2 star f. So this can be written as star of alpha T1 plus beta T2 is equal to alpha T1 star plus beta T2 star. Okay. So we know that psi t is equal to T star. So this can be written as psi of alpha T1 plus beta T2. Okay. This is this one. Alpha T1 star plus beta T2 star, and this can be written as alpha psi T1 plus beta psi T2. Okay. So psi alpha T1 plus beta T2 equal to alpha psi T1 plus beta psi T2. That is, psi is linear. To prove psi is 1 to 1, let psi T1 is equal to psi T2. Then we get T1 star equal to T2 star as per the definition of psi t. Okay. So this can be written as T1 star minus T2 star is equal to 0. Okay. So this implies that norm of T1 star minus T2 star is equal to 0, because We know that norm x is equal to 0 if and only if x is equal to 0. So using equation 7 and choosing alpha is equal to 1 and beta is equal to -1. Okay, this one. Then we have star of T1 minus T2 is equal to T1 star minus T2 star. So from equation 7, by choosing alpha is equal to 1, beta is equal to -1, norm of the star of T1 minus T2 is equal to 0. And also we know that from above, norm of T star is equal to norm of T. So we can write this is norm of T1 minus T2 star, that is norm of T1 minus T2. Okay. So norm of T1 minus T2 star is equal to 0. This implies that norm of T1 minus T2 is equal to 0. This implies that T1 minus T2 is equal to 0. This implies that T1 is equal to T2. Hence, psi is 1 to 1. This proves that psi is an isometric isomorphism on Bxy to By star x star. Now we prove psi reverses the product. Okay, that is, we have to prove reverses the product, that is star of T1 T2 is equal to T2 star T1 star. Let us prove it. For all x belonging to x and f belonging to y star, we have star of T1 T2 f x is equal to f of T1 T2 x as per the definition of the adjoint. Okay. So T1 T2 x, that is the meaning of the T1 product of the T1 and T2. Okay. So that is composition of T1 and T2. That is, this can be written as f of the T1 of T2x. Again, this can be written as T1 star f T2x. Okay. Again, we apply this, the adjoint of T2 star. Okay. So this can be written as T2 star of T1 star fx. That is T2 star T1 star fx. So this is equal to this. So we can write star of T1 T2 f is equal to T2 star T1 star f. Again, this can be written as star of T1 T2 is equal to T2 star T1 star. Again, as per the definition of psi t, that is psi t is equal to T star. So this can be written as psi of T1 T2 is equal to psi of T2 into psi of T1. Okay, that is the reverse product. Psi preserves the identity. Finally, if I is the identity operator, then I star f x, as per the definition of adjoint, we can write this f of ix. I is the identity operator, so it can be written as f of x. So f of x can be written as I f x because I is the identity. So comparing this and this, that is I star f equal to if. That is I star is equal to I. And again, using the definition of psi, this can be written as psi of I equal to I. Thus the theorem is completely proved. In this lecture, we have discussed the conjugate of an operator, that is conjugate of a transformation. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Narisi. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publisher, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.